am recording. And I'm going to choose. And then, okay. So last time we were talking about, well, we talked about a lot of things. So we talked about momentum, which is equal to mv. We talked about impulse, which has that funky unit J. And impulse is actually equal to a whole bunch of things we found out, right? So what's one of those things that impulse is equal to?
F theta t.
Say it again.
It is the for P or J.
For J.
Okay, so it is F times theta t.
Oh, F times dt.
The change of the time.
Okay, delta t.
Okay.
There we go. And you said exactly what I thought you said. It was just kind of weird because I didn't understand what F theta t meant, but we got it. Okay, so actually we're going to come back to this one in a minute. So what else is J equal to? Annabelle?
Change in P.
Okay, so it's equal to the change in P. And then we also said that it was equal to an integral, right? It was equal to the area under the curve between whatever two times we were talking about, f of t dt, okay? And so this, like we said, is usually the area under the curve. And all of this put together gives us that impulse linear momentum theorem that I think we're going to try to test in a lab on Thursday, okay? So we're not going to be able to do individual labs, but I think we'll try to do a group lab and take one set of data, and then you guys can do another lab. Okay, so let's go back to Fiona's answer, which is this F times delta t. So, like we had in AP Calc yesterday, we know that the average value of that force is 1 over T final minus T initial times the integral from T initial to T final of F of T dt. Okay? And of course, we know that T final minus T initial can also be written as delta T. And because the integral part is impulse, it makes sense to turn this whole thing around and say that J, the impulse, is equal to F average times delta T. Okay. And we drew some pictures when we were in AP Calc yesterday and showed how if we had a straight line, if we had a line at an angle, kind of if we had a curve, that we could kind of play some games and see how that average value would give us the same area. Okay. And remember still that this is equal to delta P, so we can also say that F average is equal to delta P over delta T. Which should not come as a surprise because we kind of already went through this, right? And this was kind of something we talked about at the beginning of our derivation. All right, we good? Okay, so I think the next thing is an example problem. It should talk about a 0.3 kilogram softball. All right, if somebody could read that for us, please.
23-kilogram softball has a velocity of 12 meters per second at an angle of 35 below the horizontal, just before making contact with the bat. The ball leaves the bat at 2.0 meters per milliseconds later, with a vertical velocity of magnitude 10 meters per second as shown below. What is the magnitude of the average force of the bat on the ball during the ball-bat contact?
Okay. So, what's up? Of course. So we start with some initial momentum here. That's 35 degrees below the horizontal, okay? And I don't know where the degree mark went, but it should be degrees. Okay. And we end up with a final velocity that gives us a final momentum that's in the vertical direction. So this is kind of just redrawing your picture, and we'll let that be plus x and that be plus y. And one of the things that you gotta think about is that every time you see average force in a problem, it's probably going to involve impulse and change in momentum. Okay? So if you're reading a multiple choice question and it starts talking about finding the average force, you should start thinking about impulse. You should start thinking about a change in momentum that happens over a particular amount of time. Just like forces that act over distances should make you think about work and changes in energy. Okay, anytime it talks about average force, it's probably going to be an impulse momentum question. Okay, and this problem very specifically says, what is the magnitude of the average force? So we know that the magnitude of the impulse is going to be equal to the magnitude of the change in momentum is going to be equal to F average times delta T. And they're even so kind as to tell us that delta T is 2.0 times 10 to the minus 3 seconds. So if we could find either delta P and therefore J, or J, then we'd be able to solve this problem, right? Okay, so remember that J and delta P are vectors. So Jx is going to be delta Px, and Jy is going to be delta Py. And then once we have the magnitudes for Jx and Jy, we can figure out what the magnitude of J is. So we'll start with the x direction. So Jx means that's going to be P final x minus P initial x. And what's P final x? What? 0, right? Because where is all of the momentum afterwards? In the y direction, okay? So obviously there's got to be some force that's responsible for stopping all of the x momentum and giving us only y momentum afterwards, okay? And then I need to know what Pix is. The initial momentum is in the x direction. And how do I find that?
MV.
Oh, go ahead. What?
It is just the 0.5 kilograms times negative 0.4 meters per second.
So it's MV, but it's not just MV, right?
MVX.
Okay, so how do I get that? What am I going to multiply V times to get VX?
Cosine angle.
Okay, so cosine 35. And that's going to be in the positive direction, right? So there's some negative sign there, but that's from math, okay? It's an arithmetic negative sign. So M is going to be 0.30 kilograms. We know that it has that initial velocity of 12 meters per second times cosine 35 degrees. And that tells us that Jx is going to be equal to
I got negative 2.9 kilogram meters per second.
okay, I'm going to stick with 9.5 and just kind of keep an extra sig fig around for a while. Let's see what other people get. Okay, Annabelle agrees with Lauren. Okay, so does Dagny. All right, so that gives us a value for Jx. And now we want to find Jy. So again, that's going to be P final Y minus P initial Y. Okay. What's P final Y going to be? Or how do I write it? What's the formula for it? Okay, so it's going to be MVY final minus MVY initial. Now, all of my velocity is in the Y direction for the final part, right? So I don't have to worry about breaking it into components. It all just points up. Okay. Little more complicated for my VY, for my initial velocity, right? For one thing, what direction is that initial velocity pointing in?
Negative.
Down. Negative, yes. So that's going to be negative. Whatever that VY is, times what? Call it the initial. How do I make it into the Y component? Sine 35, says Dagny. Okay. So I want you to pop all that into your calculator and let me know what you get. What'd you get?
I got 5.06 kilograms per second.
All right. Let's see what other people got. Same thing, Dagny? Yep, so P2. All right, so now I have my components. So this, like we said before, is Jy. I want to combine those components. So my magnitude of J is going to be the square root of the sum of the squares. So what am I going to get? What'd you get, Dagny?
4.11, but this 4.1.
Okay, well, still, this is an intermediate answer, so we can leave it as
Oh, then actually
4.11,
4.1.
which is actually not what I get.
I got 5.86.
Oh yeah, I think you know what? I forgot to include the. Yeah.
Okay, what did you get, Lauren?
5.86.
Okay. That at least has a hypotenuse that's bigger than one of the sides, which is kind of important. Sophie agrees. Okay, so then we go back and we know that our F average is going to be the magnitude of J over delta T, or the magnitude of the change in momentum over delta T, but either way, it's 5.86 kilogram meters per square divided by 2.0 times 10 to the minus 3 seconds. And F average is excellent. What'd you get?
I got 2,100. Oh.
Well, kilograms meters per second squared, right? So that gives us newtons, but the units do work out. What did other people get? Okay, and that gives us our 2 sig figs. All right. So like I said before, and it bears repeating, if you're asked something about finding the average force or using the average force, it's probably referring to impulse or change in momentum, especially if that force is being applied over an amount of time. Okay. All right. We good? Okay. So like I said, we'll be using impulse change in momentum to do a lab on Thursday, I think. Okay, since we have a double and we haven't done a lab in a while, and you gotta have labs because it's what's necessary. Okay, so let's go back and look at the conservation or the momentum exploration. Okay. So you did this last Friday. You had a bunch of things that were knocking into each other. You were supposed to look at things and see if you could make some conclusions. Okay. So I think all the way at the bottom, can you draw any conclusions about momentum and velocity conservation? What was conserved? Was the velocity conserved after each collision, before and after each collision? Every time? Was it conserved sometimes? What does conserved mean? Dagny? Yeah, it stays the same. Okay, so velocity was conserved sometimes. In which situations was the velocity conserved? Dagny?
Elastic was in between both equal mass.
So it was between the things that had the same mass. So what if you had things that had different masses? Was the velocity conserved? No. How about the momentum? Was the momentum conserved for things that had different masses? Okay. Was the momentum conserved for things that had the same mass? Based on what you read for today, should the momentum have been conserved?
The total momentum should be conserved.
The total momentum. And we only have two things going at each other, right? Okay, so yes, the total momentum should have been conserved. What about the total energy? Should the total energy be conserved?
Yes.
The
kinetic energy.
Okay, should the kinetic energy be conserved all the time?
No, just in the elastic.
Yeah, just in the elastic, okay? And we're going to explore that a little bit more today and tomorrow. So, what we should have learned overall is that for a closed, isolated system, the total linear momentum is conserved. Okay. So what does closed mean? Dagny.
No external forces.
Nope, that is what isolated means. Isolated means no, it actually means no net external forces. What does closed mean? Annabelle?
Like in a closed system, like energy can't leave.
Not just energy, but something, actually it really refers to something else, not necessarily, well, maybe energy, but something else as well. Closed means no mass leaves or enters the system.
How would mass leave or enter the system?
You are riding on a sled underneath a tree. You're gliding along at a constant speed because there's no friction because it's a sled on snow. I don't know, somebody, hopefully that you know, drops a really big snowball onto your lap. So now what happens to the sled? So what happens to the sled now that it has more mass? It what? It'll go slower, okay? But in order to conserve momentum, I have to include that mass of snow in my system. Okay? So the thing is if you seem to have mass that enters or leaves your system, you need to make your system bigger to include that thing.
Or could you make your system smaller? Only focus on the part where it has.
Only focus on what?
Like if we're talking about the snowball example, could you
Yeah.
make your system just focus on the part where you have the snowball in your body?
Well, but the whole point about conservation of momentum is that I look at the total momentum before some event and the total momentum after some event. So I could certainly calculate the momentum of my system after I catch the snowball in my sled. But then I'd actually have to measure my velocity. Whereas if I know my velocity before I hit the tree, and I know the horizontal velocity of the snowball, I can calculate my velocity after the collision. Okay. So first of all, let's make a few more comments here. These are total momentum or total momenta. Okay. So it's not the momentum of individual objects. It is the momentum of the whole system of objects. And I and F refer to before and after some brief event. And that's a big part of this that isn't emphasized so much in this book, is that you're talking about something that happens quickly. So it's very easy to talk about two pool balls that bounce off each other. It's easy to talk about bumper cars bumping off each other. It's easy to talk about catching the snowball. Okay? We can also talk about, although it's kind of wacky, we can talk about taking a gravity assist, having a satellite that whips around Jupiter and picks up some speed. That's a collision. It's not things hitting each other, striking each other, but it's an interaction, it's an event that happens for a short period of time. And that's how we got like the Voyager spacecraft out into the outer solar system, is they went by Jupiter, took some pictures because we never had any before, and they were able to gain some momentum because of an interaction. Okay. So if I had to say the one concept that was the most prevalent on the AP exam, it would be conservation of momentum. Okay, it feels like everything on the AP exam comes back to conservation of momentum. There are whole ways to teach AP physics so that instead of talking about Newton's laws and talking about energy, you start by talking about momentum and conservation of momentum. So it is an equally fundamental, equally important concept. So let's do a couple of examples here, and we'll see where that takes us time-wise. Class is over at 1:30, so we still have plenty of time to probably do 2 examples. What? You're getting glass? I'm so happy for you. Yeah, but it's been going on for like over a trimester.
It's karma for when she pretended she needed glasses when she was little and then never wore them.
Okay, so example 1. Somebody read us example 1 while I copy the table. So I can get that to go in.
A mechanical fluid slides along the axis on a frictionless surface with a velocity of negative 0.4 meters per second I. When 2 internal springs separate the fluid into 3 parts, as given in the table, what is the velocity of part A?
Okay, so I don't know, I have my table. It's not in color and I can't make it bigger or smaller. So there's no friction, which means we really don't have any external net forces. Okay, this is all happening on probably a table or the floor. So yes, there's a gravitational force, and yes, there's a normal force, but those 2 forces balance each other out. Okay, so they don't have to worry about those. And if there is no net external force, and as long as I make sure my system includes particles A, B, and C, then I can have conservation of momentum. Okay, so conservation of momentum is pretty good for drawing, is a pretty good reason to draw a picture. Okay, so I have my object initially. It is moving, what, negative 4.40 meters per second I. Okay, so this is what I would call my initial case. And then in my final case, I have particle B is moving this way. Let me draw that a little bit better so you can see. So I have particle B is moving that way at 0.20 meters per second I. Particle C is moving this way at 0.30 meters per second I. And then I have particle A. Which way do you think particle A is going to go?
To the left.
And that would be positive or negative, Lauren?
Negative.
Negative. Why? Why do you think that?
Because due to conservation of momentum, you know that the initial momentum has to equal the final momentum, and the initial momentum is negative. So the particle A would have to move at a greater magnitude in the negative direction. So that way, when it is combined with B and C, it will equal the initial momentum.
Yeah. Okay, so everybody see that the initial momentum is all in the negative direction. Capital M, which is all of my parts together, is moving in the negative direction. So if the total momentum before or the total momentum initially is in the negative direction, then the total momentum after has to be in the negative direction too. However, particles B and C are moving in the positive direction. So like Lauren said, particle A is going to have a pretty big velocity to make up for, to balance all that positive momentum, and then still give us a net momentum in the negative direction, okay? However, we are not going to assume that A is moving in the negative direction. Because if we do that, you have to remember a bunch of things. And I love you all, but you're not going to remember them. And especially when you're sitting for the AP exam and panicking, you're going to panic, okay? Even though you shouldn't, but you might, okay? So we're going to fall back on one of my axioms, which is you always let your unknowns be in the positive direction. And then if you're wrong, they pop out with a negative sign and life goes on. However, if you had let the A go in the negative direction and it popped out with a positive sign, that would have meant, yes, you chose correctly. It is in the negative direction. That it popped out with a negative sign, it would have been, no, you chose incorrectly. It's in the positive direction. You never would have remembered that. I love you, but you wouldn't. Okay? So it's better to just always let your unknowns be in the positive direction. Okay? We know in our hearts that we want VA to be in the negative direction. That's going to be our reality check after we do the problem. Okay? We good? We got it? All right. So, because this is a closed isolated system, I can say that the total momentum initially has to be equal to the total momentum finally. I myself, in my heart, know those are capital P's. You may not know that, so I'm just writing total. Okay. Initially, I've just got my total mass times some initial velocity. But afterwards, I have the momentum of each of my particles. So that's what I mean by total momentum, is I add up the momentum of each of the particles, all of the particles. So that's going to give me MVI, and then I'm going to have MA, we'll call it VA, plus MB, plus MC, VC. And I know these are all in the plus or minus X direction, so I really don't have to worry about the vector symbols. And since A is the only thing I don't know about, I'm going to move everything else to the other side. So I'm going to have MVI minus MBVB minus MCVC is going to be MAVA. And then I just divide both sides by ma. And I can sub in. So VA is going to be capital M. How do I find capital M? Yeah, I add all the masses together, right? Which looks like it gives me 1.30 kilograms. Okay, I know that that velocity is negative 0.40 meters per second. Not going to worry about the I's anymore, okay, because like we said, everything is along the XY axis. Minus MB, which is 0.60 kilograms, times VB, which is 0.20 meters per second, minus MC, which is 0.20 kilograms, times its speed, which is 0.30 meters per second, all over the mass of A, which is 0.50 kilograms. And when you work your calculator magic, we get what?
Negative 1.4 meters per second.
Okay, so Fiona got negative 1.4 meters per second. Let's see what other people got. Dagny's agreeing, Sophie's agreeing. Okay, and it turns out to have a negative sign, which means the positive direction that we gave it was wrong, which we expected, and that it's in the negative direction. It's kind of big compared to the rest, which is what Lauren predicted. And it makes sense with what we were thinking. Okay. You good? All right, so example 2. Which is very similar to a problem that was in your book, but I don't remember if I told you you had to read it or not, because it's very similar to a problem that was in your book. So if somebody would read it for us, please. Should start with meteor crater.
The meteor crater in Arizona is thought to have been formed by the impact of a meteor with Earth's sun 20,000 years ago. The mass of the meteor is estimated at 5 times 10 to the 10 kilograms, and its speed at 7,200 meters per second. What speed would such a meteor give Earth in the parallax?
Okay. So another thing, every time you hear the word collision, you should be thinking about momentum. Okay? If they talk about a collision in a problem, the first thing you should be thinking about is conservation of momentum. So I know that my asteroid and my Earth are going to collide. I want to think about conservation of momentum. In order to conserve momentum, I have to have a closed, isolated system. Remember, closed means that I don't lose any of my mass or gain any mass. So what does my system need to be? What am I trying? Oh, go ahead, Tia.
Is it the meteor and the Earth?
Yeah, it's got to be the meteor and the Earth, because those are the things that are going to stick together and have a speed afterwards, right? Which I believe is what we're trying to find. Okay, that if they stick together, what are we going to have? So I'm going to have my meteor Actually, until it enters Earth's atmosphere, it's a meteoroid, as maybe Sophie and Eva remember. So this is going to be my before, or my initial case. We're going to take this, for simplicity's sake, in the reference frame where the Earth is at rest. Okay, because if not, it's going to get really ugly. Okay, which means that only the meteor has an initial velocity. And since I'm out in the middle of space, I'm going to orient my x-axis in the direction that my meteor is coming in from. Okay. And then my final situation is I still have the Earth. It really didn't get bigger. I still have the Earth, but now it has a meteorite stuck in it. And those two things are going to move off together with some final velocity. So my system is the meteor and the Earth together. And because there are no external forces, there's no friction going on here, everything that's happening is internal to the system, I can say that momentum is conserved. So I can say that the total momentum of all of my objects before the collision is going to be equal to the total momentum of all of my objects after the collision. So that gives me the mass of my meteor times VI plus the mass of the Earth times 0, because we decided that the Earth wasn't really moving, is going to be equal to the mass of the meteor plus the mass of the Earth times some final velocity. Okay, so this term is just gone because it's multiplied by 0. And I want to find that final velocity, which is just going to be the mass of the meteor times its initial speed over the mass of the meteor plus the mass of the Earth. Again, everything's moving along what I'm going to call the positive x direction, so I can get rid of my vector symbols. Okay? And what direction do you expect VF to be in? Positive or negative? Assuming that this is positive. What? Positive. Why, Greg? Sure. What you're trying to say is that the initial momentum is in the positive direction. So the final momentum, total momentum, needs to be in the positive direction. Okay? So if we substitute in here, they tell us the mass of the meteor is 5 times 10 to the 10 kilograms. It was coming at 7,200 meters per second. And then we have the sum of the masses. So that's 5 times 10 to the 10th kilograms plus 5.98 times 10 to the 24 kilograms, which is the mass of Earth. Make sure you use parentheses, please. And what do you expect it to be? Big or small? What do you think? Probably small. Because that Earth is much, 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 much bigger than that meteor. Or meteorite once it hits the surface.
Dr. Goetz,
Yes.
what is in the denominator? It is 5 times 100 to the 10 or 5 times 10 to
Oh, I see what you're saying. I'll write it again, but you know what it is. It's the mass of the meteor.
the 9.
There we go. I ended up with an extra stroke. I tried to give pi 3 legs earlier today, so just have some issues. Who's got an answer? What do you got, Dagny?
6.02 times 10 to the negative 15. But would it just be 6 times 10 to the negative 15?
Yeah, pretty much. And what do you say? It's times 10 to the
Negative
13th?
Yeah.
That's not the exponent, I guess.
It is 10 to the negative 11.
Yeah, I get negative 11 meters per second. So
This is a kind of a weird question, but would you be able to account, like, could you count going through the atmosphere as a collision? Because you are, like, turning two particles to each other.
the individual particles, yes, but the overall effect, I think you would more use friction. And like terminal, well, you would use air resistance because that would have to do with the density of the air, which would be changing, and the velocity, and yeah. I don't think you would do it that way.
Also, the mass would probably change.
Yeah, which you can account for. But yeah, I wouldn't. I don't think you. I just don't think it would be effective to use momentum. Okay. So are you going to feel this? Is the Earth really going to move? No. You can't even see times 10 to the minus 11 meters. Okay. It's just not gonna. It's just not going to happen. Okay. You need something much bigger than that. All right. Okay. So, we're going to talk about collisions, and then I'm going to stop class because I don't want to stop in the middle of the equations that we're going to derive to deal with collisions. Okay. So, your book discusses 4 types of collisions, but I think there are really only 3. So what were the last 2 types of collisions that we talked about? The Earth and the meteor colliding and the toy breaking into 3 pieces. What kind of collision was that? Well, we have elastic collisions. We have inelastic collisions. And we have completely inelastic collisions. Which category does the Earth and the meteor fall into? Dagny, what do you think? Not just inelastic, but completely inelastic. Right, because so, and here's where your book and I kind of differ. Your book thinks that completely inelastic collisions are when things come together and they stay stuck together, so like the Earth and the meteor. And a separate situation is an explosion, where you have something that starts as one thing and becomes many things. I think those are both completely inelastic. Okay? So for an elastic collision, the objects bounce off each other. They begin as separate objects and they remain those separate objects. And most importantly, both total momentum and kinetic energy are conserved. So cue balls bouncing off each other. Those are elastic collisions. Probably not, because there ends up being too much friction, but in theory, yes. Inelastic collisions mean that, so it's interactions. Where only momentum is conserved. So the objects can begin as the same, as separate objects, and leave as those same two separate objects. But the kinetic energy may not be conserved for some reason. Yes?
So could you have like friction?
No, because that would be an external force. Okay? But what could happen is you could have softer balls that would deform when they bounced off each other. The thing about pool balls is that they have a very hard outside, so they just bounce off each other. But if you had, you know, like soft soccer balls or soft kickballs, anything like that, or just like bean bags or foam balls, they don't even have to be soft, as in less air. But those might deform, and so energy would go into deforming the objects and then having the objects go back to their original shape. There could be energy that's lost to sound. So perhaps those cue ball or those pool balls bouncing off each other aren't exactly perfectly elastic collisions because there's a sound. And there has to be some energy that's lost to make that clip. Okay? So it's important to understand the difference between elastic and completely inelastic collisions. Because in completely inelastic collisions, either the objects start separate and stick together, or start as a single object and become many. But either way, only momentum is conserved. So don't assume that just because objects start separate, interact, and leave separate, don't assume that's an elastic collision unless you're told. It could be an inelastic collision. But for any collision, momentum is conserved, as long as it is a closed, isolated system. And as you saw in your book, sometimes what you need to do is really narrow the time that you're looking at your object to right before and right after the collision so that you can consider it a closed isolated system. Okay. All right, then what we're going to do tomorrow is we're going to look at elastic collisions and develop some important results that are worth remembering. Okay, and then we'll do some examples, maybe not until Friday, especially if we do that lab on Thursday. Okay? All right then. I'm going to exit the Zoom. So Fiona, you'll have to come back. Lauren, have a lovely day.